Right, we are looking at a concept of what we call Karnaugh maps. Karnaugh maps, and we let f of x, y, and z be x primed and y and z, or x and y and z. We need to simplify the function f. Right, so to simplify the function f, we evaluate the function f at these different sets of values of x, y, and z. For example, if x is 0 here, we take not x, which is a 1, and 0 and 0, which is a 0. And if you have 0 and 0 and 0, you get a 0. And therefore, the result here becomes a big 0. Okay, so now we're going to write here a 0. Since a 0 or a 0 is a 0, now if you put this set of values here in the place of x, y, and z, not x is a 1 and 0 and 1, it's actually a 0. And if you have here a 0 and a 0 and a 1, the result is obviously a 0, like so. Next, if you put in here 0, so that we have not 0, you have a 1 and a 1 and 0, or 0 and 1 and 0, you have a 0. Next, if you have not 0, you have a 1 and a 1 and a 1, which becomes exactly a 1. Right, it becomes a 1 because then if you have here a 1, and a 1, it becomes a 1 because not 0 is a 1. So a 1, a 1, a 1 becomes a 1. Or you have a 0 and a 1 and a 1. Okay, so you have that. So this becomes a 1. Next, if you have not a 1, that's a 0 and a 0 and a 0, which becomes a 0. Or if you have a 1 and a 0 and a 0, so that becomes here a 0. Next, if you have this one here, not a 1, it's going to be a 0, and a 0 and a 1, which is a 0. Or if you have a 1 and a 0 and a 1, it becomes a 0, like so. Next, if you have a 1 and a 1, right, 1, 1, 0. So if you put it here, it's going to be not 1, which is 0, and 1 and 0, which is 0. And here, if you have 1, 1, 0, you get a 0. Okay, so this is a 0. Next, if you have this one here, which is not 1, so it becomes a 0, and 1 and a 1, which is a 0. And if you have all the ones here, a 1 and a 1 and a 1, it becomes a 1. Now we come in to complete the Karnaugh map of F. This one here is the truth table. Right, is the truth table of F. Right, so here in this block here, you have not X, not Y, not Z. So you're looking at this block here, this not X, not Y, and at the bottom we have not Z, and that is the 0, 0, 0, and that means you put a 0 here. Next, in this block here, this corresponds to this row of not X, not Y, and Z, so it's 0, 0, 1, and the result is a big 0. So this one is actually a 0, a 1, and a 1. So in other words, if you have this one here is 0, 1, 1. 0, that's not X, a Y, and Z. So it's 0, 1, 1. 0, 1, 1. It's a 1. So you put a 1 here. Next, you come here. We have not X, Y, and not Z. So it's 0, 1, 0. 0, 1, 0. It's a 0. It's a 0 here. Next, you come to this one. This one is 1, 0, 0. 1, 0, 0 is a 0. 1, 0, 1. 1, 0, 1, because it's X, Y primed, with Z. 1, 0, 1. 1, 0, 1 is a 0. A 1, 1, 1. Right, so you come to this one here because it's X, Y, and Z. 1, 1, 1. Okay, corresponds to the bottom row, and that is a 1. This one here is a X, Y, and Z primed, so it's a 1, 1, 0, which is a 0. Like so. So we have actually completed this particular Karnaugh map. This particular array is called the Karnaugh map of F. So we have completed that one there, and we continue with analysis of these problems. And in particular, we are attempting to solve and simplify the function f in the process. So let us proceed and see what we can do here. Right, we proceed and we see what we can do here. So we actually proceed to solve this problem. Right, on this side, we still have our Karnaugh map, which we actually have just completed. We got a 0 here, we got a 0 there, we got a 1 here, we got a 1 there, we got a 0 here, got a 0 there, we got a 0 here, we got a 0 there. So these are the things we got. Right, so this one here is called the Karnaugh. Right, it's called a Karnaugh map of F. So what is the simplified expression of the function here? Right, so the simplified expression becomes f of x, y, z. It's exactly the same as x primed and y and z. Or x and y and z. It's exactly the same errors. Okay, so at this point, you need to analyze this and analyze it very, very carefully. But what we are able to see is that this one here corresponds to, for instance, a part of y, but also because a part of the y block, but also a part of the z block. So now what we do is we look at a possible association of the entries there. Right, so or a possible decomposition of the y of the one values. We focus on the one values, and we're able to see therefore that we can actually have this particular sort of decomposition of the one values. But this here is in the y block, but it's also in the z block, and therefore this simplifies to exactly y and z. It simplifies to y and z, and that is the answer. So we look at the next point. Right, in the next point here, we are looking at the following, but also we note that this one here is nothing other than the truth table of the function of three variables, x, y, and z. Let f of x, y, and z be the Boolean function whose truth table is shown below. Write down a simple expression for f. Okay, here at this point, the truth table has already been completed for us. And what we just ought to do is to just carry this information forward into the Karnaugh map. For example, this is x primed, y primed, z primed, so it's 0, 0, 0, and the result is a 1. So we put a 1 here. Next, we come to this one. This one, it corresponds, this block, for instance, corresponds to x primed, y primed, and z, so it's 0, 0, 1. Right, 0, 0, 1 is a big 0. Next, you come to this one, which is 0, 1, 1. 0, 1, 1 is a 0. Next, you have this one, which is 0, 1, 0. 0, 1, 0 is a 1. Next, you come to this one here, which is 1, 0, 0. Right, 1, 0, 0 is a 1. This one corresponds to this particular cell here, corresponds to x, y primed, and z, so it is 1, 0, 1. Right, so 1, 0, 1 corresponds to a 0. This one corresponds with x, y, and z, so it is 1, 1, 1. And that corresponds to the 1, 1, 1 has the value of the function as a 1. This one corresponds with x, y, z primed, so it is actually 1, 1, 0. 1, 1, 0 is a 1, so you put a 1 here. So we have got this particular Karnaugh map of f. We proceed to analyze the Karnaugh map of f. So this here is the Karnaugh map of f. Okay. Now we just completed this and we got a 1, a 1, a 0, a 0, 0, 1, 1, 1. Now let's analyze this with much care. Right, so this is pretty straightforward, but we need to look at a possible association of decomposition of the ones. So this here is a possible decomposition of the ones, like so. We proceed to analyze this further and look at what this means. And we need to analyze and see any possible decomposition of the ones. Right, so how do we sort of decompose the ones in this particular instance? So let's look at these together and analyze these here. Right, analyzing these which much care and much caution. So you'd have that, but also you'd have the particular association here. But I want us to look at the fact that this one here, this can be seen as the Z primed block, and also this is the Z primed block. So let's just do this. Right, let's just do this. Because it's a Z primed block and it is Z primed here, it is Z primed there. So it is common practice for us to just do this for this part. We just try to write clearly here. So it is a possible way for us to have this like this, and you have it like this, and you have it like so, so that also this side here, you have it like this here, and you also have it like so. Right, so now let's look at these, but look at these very, very carefully. What else do we need? But what does this symbolize for us? Because we are looking at these, but we must look at it very carefully. So these Z primed and the Z prime sort of meet up, but also now So in other words, if we like fold this, because these are both Z prime, so we draw this particular decomposition of the ones in a way that will sort of be to the end and to the end, such that even if you fold these to form a cylinder, if you look at these as a two-dimensional um, piece of material that can be folded into a cylinder, such that this end actually meets this end here, you'll be able to see that the Z primed will meet the Z primed there. Okay, so simultaneously we're able to see that this here is is another it is another obviously decomposition of the ones. So you have another decomposition of the ones like this, and now you have this. Okay, so you have exactly that. Just terminate this one here. Let us just terminate this one here. So you can have this one coming to the end here like this, and this one coming to the end like this one coming to the end like this. Okay, my friends, now let's look at this very, very carefully. What else do you see? This is a possible decomposition of the ones, but what does this mean? So if you look at the fact that this one here, together with this part and this part constitutes the Z primed block, but it's like a full Z primed block because this was like a portion of the Z primed and this another portion of the Z primed. So this is like a full Z primed block, but also it actually, therefore, you can see that it meets also the other one. What other part does it meet? So it also meets, it meets this part here. There's an intersection with this part of X and Y, because this is like Y, but it's actually an intersection of X and Y. So which means that the function here, X, Y, and Z, this function is Z primed and X and Y. Is actually this one is the full Z primed. So it becomes Z primed or X and Y, right? Because we have the Z primed here, or we have the intersection of the X and the Y. X and Y intersect here, or the Z primed, which is at the ends of this. Okay. Now, there are a couple of things we need to look at here. So this is a possible simplification of the, or is a possible decomposition of the of the one values in this particular kernel map. Right. So next, we actually are able to still see something interesting here. This is the truth table of F. Truth table of F. So let f of x, y, and z be a Boolean function whose truth table is shown below. Write down a simple expression for f. Let us actually fill this up here and see what we get. For example, this one here is the x primed, y primed, and z primed block, and x it's actually now the 0, 0, 0. So 0, 0, 0 is a 1. Next one is x primed, y primed, and z. So it's 0, 0, 1. 0, 0, 1 is a 1. X primed, y, and z is 0, 1, 1. 0, 1, 1 is it's a 1. This one is x primed, y, and z primed. So it is 0, 1, 0. So 0, 1, 0 is a 0. Then you come to this one, which is x, y primed, z primed, which is 1, 0, 0. So 1, 0, 0, it's a 1. This is x, y primed, and z. So it's 1, 0, 1. So 1, 0, 1 It's a 0. Next, we come to this one, which is corresponding to the X row, Y, Z. So it is 1, 1, 1. 1, 1, 1, it's a 1. So you come to this one here, which is corresponding with the X, Y, Z primed. So it's 1, 1, 0. So 1, 1, 0, it's a 0. Now we have this. Okay, so just take a look at that part. So this one here is 1, 1, 1, 0. Okay, so yeah, it's like 3 ones and 0, and then 1, 0, 1, 0. 1, 0, 1, 0. Now, this is the Karnaugh, right? The Karnaugh map of F, right? So in terms of this, what is the meaning of this Karnaugh map, but also what is the purpose of the Karnaugh map? A couple of things remain very important for us. We analyze this with F of X, Y, and Z. So this Karnaugh map is as follows. So if you look at these, if you look at these very, very carefully, we have a possible decomposition of the ones. We can put these ones together, but also we can proceed to put these ones together because these ones here sort of correspond with the they correspond with the Y primed block. So these ones here, they correspond with the Y primed block, so we put them together. But these ones here, they're part of the Y prime block. We put them together. Okay, so we have this one here. We put them together like this. Right, so we can put these ones together here because they correspond to the they correspond with the Y block. They're just a part of the Y block, so we actually put them together like that. Just to do that. So if we actually therefore put them together here, so what is the answer to this here? Right, so the answer to this is as follows. Right, so look at these very carefully, you'd see therefore that this one corresponds with the Y primed block, but also it actually meets the Z primed block, so it is corresponding to Y primed and Z primed. Or now, if you look at this one here, it corresponds with the X primed, but also the Y primed as well. So it is X primed and Y primed. Or at this point, you have this one, which is the Y and the Z. So it is Y and Z, like this. It is Y and Z. Y and Z. It is Y and Z. Okay, so now we have this, and this is the simplified result. It's one possible decomposition of the ones that can be obviously made, and there are many other possible decomposition of the ones. So we have here the results obtained from the Karnaugh map. Now, the couple of things that obviously can be analyzed here, and we can always look at that. And also, in this case, so this Karnaugh map has 2 rows, 1, 2, 1, 2, 3, 4. So it is sort of a 2 by 2 array of zeros and ones. It is a 2 by 2 array of zeros and ones. Right. So the 2 by 2 array of zeros and ones is called the kernel map of F. So a kernel map of F by definition is a 2 by 2 array of zeros and ones. That is what a kernel map is. Next question. A further look at kernel maps reveals that we can master kernel maps also for functions of two variables. Let's look at this particular case here. At this point, we are looking at the function f of x and y, which is x primed and y primed, or x primed and y. Right, so we have 0, 0. So if you have 1 and 1, it's a 1, 1 and 0. So you get a 1 here. Here you have, so let us make a small change here. Right, so I want to remove something here. Going to make a small change. So this one here must be a 1. So just note that. Right, so it must be a 1 here. It must be a 1. Let me see. And this one must be, so it's 0, 0, 0, 1, 1, 0, 1, 1. Right. Okay. So this one must be, okay, 1, 0. Okay, good. So this one is 0, 0, 0, 1. And this one must be 1, 0, 1, 1. Okay, just to complete this properly. So this one is 0, 0. The next is 0, 1. This one is 1, 0. And this one is 1, 1. So up as you can see, 2 zeros, 2 ones, 0, 1, 0, 1 is the correct, yeah, it's the correct truth table of F. So this one becomes the truth table of F. Now, a couple of things that we need to learn here, like if you put here the 0, 0, here you have not 0 and not 0, it's a 1. Or this, which is a 1. So here you come here, not 0, it's a 1, and 0, which is a 0. But here you come and say not 0, it's a 1, and a 1, which is a 1. Put a 1 here. Next, you come here, this one is a not 1, which is 0, and 1, 0, and then you come here, this one is 0, and 0, you have a 0. Right, here you come, this one is not 1, which is 0, or not 1, 0, and 1, which is 0. Right, so this particular part of the array, which is called in this case, it will be a 2 by 2 array of zeros and ones. And the 2 by 2 array of zeros and ones constitutes what you call a Karnaugh map of F. This is 0, 0. So 0, 0 corresponds with the 1. And then this one corresponds to 0, 1. 0, 1 is a 1. And this one corresponds with 1, 0. 1, 0 is a 0. So one corresponds with X and Y, which is 1, 1, which is a 0. So we have just completed the Karnaugh map of F. And this Karnaugh map of f then means that we can write the function x and y, which is exactly from here, from the top here, we were given the Boolean function x primed and y primed, or x primed and y. And this Boolean function has particular symbolism. So we have, therefore, that this here is what we get. And so if we have this one is exactly x primed, it is the entire x primed row. Obviously, the x primed row has particular changes from x y primed to y. So the answer to this becomes exactly x primed. So this is x primed. Okay. And then we have simplified f. We have simplified f. And so the simplification of f using what we call Karnaugh maps is only x primed. Okay, we good, but we continue to look at more Karnaugh maps. Let's just edit this here a little bit and look at a simplification of this, but I need to edit the these particular entries in the truth table of f. Right, need to edit in the truth table of f so that we can continue. And then now we can even edit these, but I'm going to fill them up. Okay, we check everything, but we need to make sure that this is correct. So now using the Karnaugh map of f, we have what? So this is 0, 0, 1. This one is 0, 1, 1, 1, 0, 1, 1, 1, 1. So this is going to be 1, 1, 0. Okay, at this point, the truth table of f has been given. So this is the truth table of f. So you see, the truth table of f has been given. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, the truth table has been given. Here we are looking at, for instance, not x, not y. So this corresponds with the 0, 0 row of the truth table. So the 0, 0 row actually corresponds with the value 1 of the function. So we put 1 here. And then now this one is x primed and y. So it's 0, 1. 0, 1, it's a 1 here. Next, we have this one, which is x, y primed, which is 1, 0. 1, 0 is a 1. And then here, this one is x, y, which is 1, 1, which is 0. Next, we look at this simplified expression of the Karnaugh map, but also let's first look at the possible decomposition of the 1 values. So the 1 values here, the ones can be associated this way because this corresponds to the y primed column. So, but this one here also corresponds with this particular row of the x prime. So in the end, then we're able to see something that f of x, y is the same as what? Right. So let's look at the possible simplification here. So this one here is the entire y primed. So we can just write y primed there. Okay, because this is y primed. Right. Or, but you also have this one here, which is obviously it constitutes a couple of things. But what does it then constitute these? Right, so let us look at these, but look at these very, very cautiously and very, very carefully and see what we've got. Right, so the question then becomes, what is the result here? Okay, so the couple of ways obviously you can use to simplify this, let me just write that out very well. So we can see that this corresponds with y primed, right? But this corresponds with the x primed row. So you can write this one as x primed or y primed. Okay, so this is correct. This is exactly correct, x primed or y primed. So this is correct. Like this is the x primed row, all of it, or the y primed column, all of it. Okay, now this is what we get. And we can obviously look at other possible decompositions. We can analyze this and say the following. Right, so we can look at this particular decomposition. Right, and then you can analyze this like this. And then you have okay. Right, so you have this one here. Right, so another possible decomposition of the ones is somebody can say, okay, this is just the ones, and then you can also have this. So that is a possible decomposition of the ones for this one, where we say it is the entire x primed, y primed, and you come to this one, and you say the fxy is actually this one here, which is can be seen differently. How else can it be written differently? So this would be, for example, your y primed column, or this one would be like your x primed and y, x primed and y, x primed and y, right? X primed. So this is y primed. Y primed is this. So this particular kind of map corresponds with this particular simplification, or this decomposition of the ones yields that one. So, but we also have another decomposition of the ones like this that produces this particular simplification of the Boolean function. So these particular decomposition of the one values are the same, or rather yields functions that are equivalent, but these two functions look different, but yeah, they are equivalent to each other, okay? Because these functions yield the same truth table, okay? They produce the same truth table. So yeah, we have that, and we are done with the discussion on these Boolean functions. And yeah, thanks everybody for joining us, and goodbye.